Welcome back, everyone. In our previous lecture, we introduced the fundamental mechanism of Raman scattering. We explored virtual states, Rayleigh scattering, Stokes lines, anti-Stokes lines, and the Raman shift. Today, we are going to ask a deeper and more important question. Why are some Raman bands extremely intense while others are weak or even absent? What physical property controls Raman intensity, and when we measure Raman peaks area computationally, perhaps using Python, MATLAB, or Origin, what molecular property are we actually quantifying? So before we answer that question, let us briefly compare Raman spectroscopy with infrared spectroscopy. In IR spectroscopy, a molecular vibration is active only if it is produces a change in dipole moment. That is the key IR selection rule. For example, oxygen-hydrogen bond stretch is strongly IR active because the vibration produces a large dipole change, but highly symmetric vibrations often become IR inactive. Raman spectroscopy follows a completely different rule. For a vibration to be Raman active, the vibration must produce a change in polarizability. This is one of the most important concepts in all Raman spectroscopy. So let us understand it carefully. A polarizability refers to how easily a molecule's electron cloud can be distorted by an external electric field. Imagine the electron cloud surrounding a molecule. Some electron clouds are soft, diffuse, and easily distorted. Others are compact, tight, and resistant to deformation. Consider two extreme examples. A heavy atom like iodine possesses a large diffuse electron cloud. Its electrons are relatively far from the nucleus. That cloud can deform easily. Therefore, iodine containing molecules are highly polarizable. Now compare that with the fluorine. Fluorine holds its electrons extremely tightly. Its electron cloud is compact and rigid. Therefore, fluorine containing molecules are much polarizable. Now let us connect this idea to Raman scattering. When the incident laser beam strikes the molecule, the oscillating electric field of the light continuously pushes and pulls on the electron cloud. This induces temporary dipole moment. If a molecular vibration changes, how easily that electron cloud deforms. Then the induced dipole changes during the vibration. That vibration becomes Raman active. Notice the contrast between IR and Raman spectroscopy. Does the vibration change the permanent dipole moment? Does the vibration change the molecular polarizability? That difference explains why Raman and IR are complementary techniques. Some vibrations are strong in IR but weak in Raman. Others are weak in IR but extremely strong in Raman. In general, highly symmetric vibrations tend to produce large change in polarizability. Therefore, they are often strongly Raman active. This is why symmetric stretching modes frequently dominate Raman spectra. Consider molecules like N2, O2, or Cl2. These molecules are IR inactive because their vibrations do not change dipole moment, but their electron clouds deform significantly during vibration. Therefore, they can produce strong Raman signals. Now, let us discuss quantitative analysis. The intensity of a Raman band depends directly on the concentration of the Raman active species. Unlike IR spectroscopy, which follows the logarithmic Beer-Lambert relationship, Raman intensity is approximately linearly proportional to concentration. That makes Raman spectroscopy extremely useful for quantitative chemical analysis, solution monitoring, and pharmaceutical assays and reaction kinetics. Another crucial factor controlling Raman intensity is the excitation frequency. The Raman scattering power increases with the fourth power of excitation frequency. Mathematically, I is proportional to nu raised to 4. This relationship is extremely important. It means higher frequency lasers produces dramatically stronger Raman signals. For example, a blue laser generates a much stronger Raman signal than a red laser. Why? because blue light possesses much higher frequency. Since intensity scales as the frequency raised to the fourth power, even a moderate increase in a frequency produces a massive increase in a signal strength. However, this creates a practical problem. High frequency lasers often trigger fluorescence, photochemical degradation, or thermal damage. Biological samples especially can burn or decompose under intense blue or ultraviolet lasers. Therefore, real Raman instrumentation always involves a compromise between signal strength and sample preservation. Modern Raman systems commonly use 532 nanometer green lasers, 633 nanometer red laser, or 785 nanometer near IR lasers. Near IR lasers produce weaker Raman signals, but they dramatically reduce fluorescence. Now let us move to the one of the most elegant analytical tools in Raman spectroscopy, that is the depolarization ratio. The concept allows us to extract not only vibrational energy information but also molecular symmetry information. Suppose we irradiate a sample using a polarized laser beam. The electric field oscillates in a one preferred plane. Now we observe the scattered Raman light. Interestingly, the scattered light is not always the polarized in the same direction. Some vibrations preserve polarization strongly, others scramble it almost completely. We measure this using polarizing filter placed before the detector. We define the polarization ratios as shown in the presentation. Why is this important? Because the depolarization ratio directly reveals the symmetry of the molecular vibration. Now, let us interpret what these ratios mean physically. High symmetric vibrations produce low polarization ratios. During the totally symmetric stage, the molecule shape remains highly ordered. The electron cloud expands and contracts uniformly. As a result, the scattered light remains strongly polarized in the same direction as the incident beam. Those are called as polarized Raman bands. Now consider asymmetric stretches or bending motions. These vibrations distort the molecular electron cloud unevenly. The molecular polarizability changes direction dynamically. As a result, the polarization of the scattered light becomes scrambled. The perpendicular intensity increases significantly. These are called depolarized Raman bands. The depolarization ratio provides direct experimental evidence about molecular symmetry. This is incredibly powerful in group theory, normal mode analysis, and molecular structure determination. Now let us consider a classic example of carbon tetrachloride. This molecule possesses perfectly tetrahedral symmetry. Its Raman spectrum contains a strong band near 459 cm inverse. When scientists measure its depolarization ratio, they found it rho is equal to 0.005, which is almost zero. This immediately tells us the vibration is totally symmetric. Physically, this corresponding to molecular breathing mode. All four chlorine atoms move outward and inward simultaneously. The molecule expands and contracts symmetrically. Now examine the bands near 218 cm inverse and 314 cm inverse. These exhibit depolarization ratios around 0.75, which is very high. That tells us immediately the vibrations are non-symmetric bending motion. Notice how much information we extracted from the polarization alone. We did not merely determine the vibrational energy, we determined the geometric symmetry of the vibration itself. That is why Raman spectroscopy is such a powerful structural tool. So let us summarize today's lecture. We learn Raman activity depends upon changes in molecular polarizability. We explored electron cloud distortion, laser-induced dipoles, concentration dependence, laser frequency effects, and fluorescence trade-offs. We then introduce the Raman depolarization ratios. We learn symmetric vibrations produce low depolarization ratios while non-symmetric vibrations produce high depolarization ratios. Finally, we used carbon tetrachloride as a textbook example of polarized and depolarized Raman bands. In our next lecture, we will extend these ideas into rotational Raman spectroscopy. We will study how rotating molecules scatter light, introduce the rigid rotor model, and derive the rotational Raman selection rules from quantum mechanics. Thank you for watching. I will see you in the next lecture.